streaming and audio is on. I forgot to turn on the recorder last Thursday in the assembly programming class. Some of you are in that class too, and that kind of sucked because that was a good lecture. Hmm? I'm recording now. That's why I double checked. All right, so the battery will last another 2 hours and 49 minutes. I think we're good there. Um, all right, so we'll go ahead and get started with this class. I was doing something really fun in um, mobile app programming. So let's get out of that context back into here. All right, so what we'll do today is we're going to take a look at the A-star algorithm again, and this time we'll just kind of run it through, using one example, and then you guys can ask questions, about the whole process of running the A-star algorithm. I also made one minor change to the algorithm itself, and I will start with explaining that because I think that will help us kind of make the connection again to the A-star algorithm. So we'll start with that. I need to close some of my tabs here eventually. more tabs and more. All right, so the one change that I did to the algorithm, which is not reflected here because it has not refreshed itself, now it is refreshed. Okay. So the one change that I did to the algorithm, is only this part, the condition of the while. So before it was kind of like while O is non-empty and for all V in big V, f of V is less than G of X. So that was what it was like before. So now I simplified to a little bit to just, while there exists V in O, okay, remember O is a set that we keep putting elements into and then we take elements out of. So as long as at least one V in O that satisfies the following requirement, then we have to keep the loop going, okay? So now the condition is simple, okay? I don't need all of the vertices to fit this requirement. I just need one of them to fit this requirement. And the requirement seems pretty easy, but we have to understand what it means in the context of looking for the shortest path. It says right here, f of v has to be less than g of x. Well, first of all, the big question is, what is f and what is g? What are those functions reporting? So does anyone remember from last Wednesday, what is the f function? F of a particular vertex v is reporting what? Between which vertices? No, it's the no short, it's the length of, it's the estimated length, okay, of the shortest path from the start vertex to the destination vertex, but going through whatever vertex you specify as the parameter. So f of v is basically saying what is the length, estimated length of the shortest path from the start vertex S to vertex V, and then from vertex V to vertex X, which is our destination. But it's quote unquote an estimate because we're using the heuristic function, the H function, to estimate the rest from V to X. So F itself is for the most part an estimation. Is that okay? So we want that to be less than G of X. Okay, fine. What is G then? What does G of X represent? It is not an estimation. It is the length because X is the destination in this case. So G of E in general is the length of the shortest path actually found from the start vertex to whatever vertex that is in the parentheses. So G of X itself is basically saying, okay, this is the length of the currently known shortest path from the start vertex to the destination. Is that okay? So why do you think this makes sense? Why can't we leave when this condition is no longer true? Even when O is non-empty. I mean, obviously when O is empty, there's nothing we can do. But what if when O is non-empty, but all the vertices in O do not satisfy this requirement? Exactly. Because if the estimated path, are already exceeding the currently known shortest path to x, then there's no hope, right? I mean, there's nothing that we can do here because we are guaranteed our estimate is what again? What is special about h? It cannot overestimate, right? It's not necessarily quote unquote underestimating, which means sometimes it can be exactly the length of the shortest path, but it is always not overestimating. So if the estimation is not overestimated, cannot be over, that means if f of v is greater than or equal to g of x, that particular path or that particular vertex, the shortest path is not going through that vertex for sure. Okay? So are we good with this new condition? Because I just want to use this opportunity to one, reconnect to the topics from last Wednesday, and then two, to kind of reconnect to the context of, how does the A star algorithm works, and what is the major difference between A star and Dijkstra's algorithm. The main difference is Dijkstra's algorithm does not make use of any heuristics, okay, but the A star algorithm does. Okay, so with that said, what we will do today is to go through an example. And examples using the A-star algorithm is a little bit more complex to set up because we also have to provide the heuristic function. Okay, so that makes things a little bit more complex. Let's go ahead and give it a try. And we'll start with a simpler example, but it is still enough to kind of illustrate, important points of the A-star algorithm. All right, so we'll start with, let's see, one, two, maybe 5 vertices. So maybe 6. We'll make it 6. So here's A. Actually, yeah, A is fine. And here's B, C, D, E, and F. And we'll call F our destination vertex, and we'll have A being our start vertex. So S is vertex A, and then X is vertex F. And then we'll set up some paths in between. We'll have A to go to B, B to go to C, and then A also goes to C. And then we'll have B to go to D, C to go to E, and then E goes back to D, and then both E and D would go to F. Okay. And then now we can set up some lengths. Well, since we're here, might as well do we'll do some loops around here. Make sure that the A-star algorithm, does not get bothered by loops. Okay. And we'll even put the edge going back, in a loop to have a cost of 0, which seems to suggest, hey, we can go back and it doesn't hurt, it doesn't do a single thing. So 2 of these would have a cost of 0. We'll make this one having a cost of 4, cost of 1, and I'm just thinking, whether I want to make this kind of difficult to deal with. So, okay. Okay, so what we have right now, those numbers are representing distances of the edges. And you can also see why this is a digraph, because most edges or most between most vertices, there's only one edge going in one direction, except for A and C. There are 2 edges, and when there are 2 edges, they also have different distances, because there's no requirement of how the distance of edges have to correlate, even though they are going between the same 2 vertices. Okay. This would be enough for Dijkstra's algorithm, but it's not enough for A-star, because with A-star algorithm, you also need a heuristic function. The good thing is you only need a heuristic function to X, or in this case, a vertex F. So we have to set up all the heuristic function from A to F, from B to F, from C to F, from D to F, from E to F, and technically speaking from F to F, but we know that one is a 0. So let's see, from E to F, what can we do? Okay, so from E to F, it only has to be an underestimate. So if you want to mislead the algorithm to consider things that it should not be considering, you can make all the long and bad choices to have a really low heuristic. But we also have to remember it cannot be more than the actual cost of the shortest path. So that means I cannot make HEF to be 4. 4 is not okay. Why is 4 not okay? Because it's longer than 3. Because there's a shorter path from E through D to F. And that path only has a distance or length of 3. Okay, so we cannot make it 4. Even though there is a direct edge from E to F having a distance of 4, we cannot use 4 as the heuristic. We have to use 3. Okay, so we'll put 3 here. DF, we can put a 0 here, maybe. And then we have CF. So right now, C actually has a shortest path the length of the shortest path is 4. And if we don't want it to, if we want to leave it for the last one to explore, we can put a 4 here, which is the exact cost of the shortest path, because we want to kind of trick the algorithm to pick something else. So we can make this one a 0, okay, because it looks good, looks really good, but it's not. AF doesn't really matter because from the start vertex to the destination vertex, doesn't really matter what its heuristic is, because we are not really even going to take a look at it much. Okay, it doesn't really impact how we choose a vertex out of big O, because it will be the only vertex in O at that time. Yes.
You said on H of E, F.
Uh-huh.
You can't pick 4.
You cannot use 4. Because 4 is already overestimating the shortest path from E to F.
Overestimating it?
It is already overestimating because the actual shortest path from E to F is through D, going to here and then there. Yeah, so you have to be careful because even though it looks like there's a single direct edge, but the single direct edge may not be the shortest path. Yep. No, you do not. I'm doing this only to make the graph more tricky, so we can actually see how it can quote unquote self-correct when we went down the wrong path. Because the heuristic is misleading, it can actually not get bothered by it and then actually find the shortest path regardless. But the easiest way to set up all the heuristic is to make it all zeros. That does not require pre-computing anything, right? Yep.
So I missed why you had DF and BF set to 0.
DF?
And BF set to 0.
Yeah, I just wanted to make the wrong choices.
Oh, okay.
Because this way, choosing B seems to be the better option compared to choosing C as an option.
But like
So
you said, we can make them all 0 if we wanted to.
you can make them all 0, but making them all 0 is not as interesting because then it becomes just breadth first search, which is Dijkstra's algorithm. It would just kind of like pick one and pick the other one. This way I'm intentionally making it choose incorrectly, but then it will find out that it chose wrong, and then we'll go back and fix it. Yep. So AF is the one that really does not matter because the heuristic is only going to change the ordering of how you pick things out of the set O. When we pick A out of O, A is the only element, so there's no ordering involved here. So as long as it meets all the requirement, it's fine. So the actual shortest path is 1, 1, 1, 2, which is 5. So we can make this one exactly 5. We can make it 0 or anything in between. Doesn't really matter. Okay? Does everybody understand why the heuristic from the start vertex to the destination vertex really doesn't matter? It doesn't do a single thing, no matter what you choose. Is that okay? Sorry? Yeah, because that's the only choice you have at that point of the algorithm. But we'll see that when we run the algorithm. So are we good with the graph and also how we chose the heuristic function values? Now, the question that was asked a little bit earlier was a good question. And I think some of you asked the question in the previous class as well. It was, how do we choose the values of the heuristic function? And the answer is, you have to pick something that's easy to compute, and yet it is informing the A-star algorithm to a certain point. So in this case, it's just set up as an example. So I'm hand picking the H values to show that the algorithm works, even if you try your best to trick it. Okay. But in reality, the way you choose a heuristic function really has to do with the nature of the problem itself, what each vertex is representing, what the edges are really representing, and whether you can find a function that's really easy to compute and yet at the same time it provides some information that will help to guide the search. So that part depends a lot on the problem that you're trying to solve. So, so with that done, we're gonna put this over here, and then we'll shrink the main algorithm window so I have space to put the actual trace. To look at the projector here, okay. And then we can use a spreadsheet to track everything else. So we'll go ahead and open up a spreadsheet. Nope. All right, so what we need to track when we are working with the A-star algorithm would be O, which is a set of vertices. It will also have the G values and the F values. But when we run the algorithm, okay, so I'm just going through the while loop here, which is the only thing that we really need to track or look at when we try to run the algorithm. So we have to choose the vertex C, which is a single vertex. We also have to choose a vertex N, which is what C is connecting to using a single edge. There's also T, which is a temporary variable. So we'll keep track of that. Outside of this, we have the functions, the three functions we have to track. One function is F, one function is G, and the last one is pref, or the previous of something. So we'll keep track of those. We got 5 vertices. Trying to think of how to represent the functions. Okay, let me save some space first, because these 3 do not need a lot of space. We'll make those smaller. Okay, 1, B, C, D, E, F. So this is for G, this is for F, and this is for previous. And then we'll shrink a whole bunch of these. This is for G again. So and I'll merge these cells so that we know visually these are all corresponding to the function G. This is for F. And then these are for previous. So we'll shrink them first and then label. These are the previous. There we go. Okay, so are we okay so far with how the trace is set up? Okay. Hmm? The context will be slightly different. If you don't like vertex C, we can change it to another name. Okay, all right. All right, so I'm going to move this one over so we can still see the algorithm. and then move this up a little bit so we can see the graph. And yep, okay, we managed to show everything so far. Good. All right, so we will do all the initialization in one shot. The G value of everything except for the start vertex is going to be all infinity, right? So I don't have enough space to write. Yeah, I do. Okay, that's fine. So we'll just say all of these are infinity. And the same thing applies to all the f functions. For the pref, everything is unknown to begin with. So we'll just use un to specify undefined or unknown. So now we have to specify the actual g value of a. Remind me again, what is the g value of a? What is it representing? The length of the shortest path from the start vertex to whatever vertex we're dealing with. Well, in this case, it's the same vertex. So what is the length of the shortest path from vertex A to vertex A? 0. So we put a 0 here. Okay, that's easy. And over to here, what is the meaning of function f? What is f of A representing? It's the estimated length of the shortest path from the start vertex through this particular vertex to the destination vertex f in this case. So what would that be? Not 0. It's 5, because we have the heuristic function telling us that, well, if you just ask me, if you want me to guess, I'm going to guess that the length of the shortest path from A to F is 5. So that's why the f value of A is going to be 5. Okay. Now in this case, 5 is actually the length of the shortest path, but it doesn't really matter. The initialization of O is easy in this case because we only start with a start vertex, which is A in this particular problem. So that's how we initialize the problem. Do we have any questions about the initialization of all the values? We're good so far? Okay. So if this is good, I'm gonna do the same trick, which is to display the heading of each column so that we can scroll through the rest without having to deal with without losing the values. Okay. And it's going to get a little bit tricky because the current value is going to be, it's not going to be easy to find that. So I'll try my best to make it easier to see the current values. All right, so now we get into the infinite loop here. And then the infinite loop is asking, is that true? It sounds like a pretty tricky question, right? So do we have at least one vertex within O such that its f value is less than the g value of the destination? So the destination x here is basically vertex f. What is g of f? G of f. G of f is infinite. Okay? So what about the f value of A? 5. Okay? Is 5 less than infinity? Yes. Okay, very good. So we can go into the loop now. So once we get into the loop, we choose a vertex. We choose the most promising one. Okay? Of all of the vertices in O, we choose the one that has the lowest f value. Do we have anything to consider here? Do we have any choices? Like, maybe we should pick this one. Wait, that one looks better. Do we have any choices? Nope. There's only one vertex in O at this point, so we have to choose A, and that leaves the O set empty because we have to remove whatever we choose. And then we have to look at all the outgoing edges from A and consider each neighbor that the edges connect to. It doesn't matter in which order. So do you guys want to go by a particular order? Top down, okay. So we'll consider vertex B first, right, as an outgoing neighbor of A. So if you choose B, okay, then we have the edge AB connecting from A to B. So how do we compute T? If you look at the algorithm, T is computed here. which is basically just asking, okay, what is the length of the shortest path to get us to vertex A, and then add the distance from A to B. That becomes an alternative path to vertex B, so that we can consider which one is shorter, right? So it takes us 0 to get to A. It takes us, an additional 4 from A to B. So the total is going to be just 4. So t is 4. If the value of t is 4, have we found a shorter path? In other words, we compare t to the current g value of b at this point. Did we find something shorter?
Yes.
Oh yeah, absolutely. Because the current g value is infinite, so that means t, which is 4, is less than infinity, so we found a shorter path. That's good. So now we get into the conditional statement because t is less than g of n. So the first thing we do is we put that into the O set. Okay, so the O set now has b in it, and then we update the previous function. Now, when you update the previous function, you have to be careful. We are not updating the previous of c, we are updating the previous of n. So in this case, we're updating the previous of b so that we remember to get to b, we came from a. Is that okay? Okay, let me show you what I mean when I actually update it. We are not updating here. Instead, we're updating here. Because we're updating the previous of b is a. We came from a, from b's perspective. Is that okay? All right. What else do we need to update? We need to update the g value. Okay, g value is easy because it's really just whatever t is, which is 4. And we also need to update the f value. Whoops, I think I updated the wrong one. Take it out. It's this one here. And then the f value, how do we compute the f value according to the algorithm? It's pretty easy. It's the g value, which is 4, something that we just calculated, plus the heuristic from b, in this case, to f. So we said from b to f is 0. That's totally an underestimate, but that's okay. It's not negative, and it's okay. So b is also, f of b is also 4 because we estimated there's no distance from b to the destination. It's okay. It doesn't sound reasonable, but it's actually okay. So now we have done all the updates within the conditional statement. Do we have any questions before we move on to the other neighbor of A? No question. T is just a temporary variable. It's right here. It's set by this little assignment statement so that we don't have to refer to g of c plus d of cn all the time. Yep. So are we good? Yep. Yes? Okay. So now we consider the other neighbor of A, which is C. And the first thing we do is to compute t. So it's kind of the same thing. We ask what is the distance to get to A at this point? 0. Okay. And then from A to C has a distance of 1. So we now have a path that has a length of 1 from the start vertex to C. The question is, well, did we find a shorter path? So t is 1, and now we compare that to the current g value of c, which is infinity. 1 is less than infinity, so we get into the conditional statement. So once we get into the conditional statement, the first thing we do is to add it to O. So O has now BC in it. The second thing we do is to update the previous. So the previous of C is also A. So we have 2 vertices that are going back to A. That's okay. It's not a problem. Okay. And then we update the g value, which is just taking whatever t is. So we take this t value and then we use it to update the g value of c. So we put a 1 here. And then we also have to update the f value. The f value is the g value plus the heuristic from, in this case, C to F. So we estimate from C to F has a length of 4. So we have 1 plus 4, which makes 5. Okay, so we put a 5 here. Oops. If I move my mouse first. Do we have any questions at this point? So we're okay so far? Okay. Do we have any other neighbors connected to vertex A? Is A leading to any other vertices? Nope. So we are done with the for each loop. And then since there's nothing after the for each loop, we now go back to the while loop here. So when we get back to the while loop, we look at vertex B and vertex C. And then the first thing we do is to say, can we get out now? In other words, have we found the shortest path? And nothing in O, is promising a potentially shorter path. What do you think? What is the f value of B? F value of B is 4. F value of C is 5. What is the current G value of the destination? Infinity, right? Well, we not only do we have at least one vertex, we actually have both vertices having f values less than the g value of the destination. In other words, we got some vertices that may actually find us a shorter path. Is that okay? So we get into the loop. When we get into the loop, this time we have to choose between B and C. So now you have to look at this line here to say, okay, now that we do have choices, which one do we choose? Remember, this is a greedy algorithm, which means it will choose whatever seems to be the most promising at that time. So which function do we look at when we try to choose which vertex? Do we look at the f function or do we look at the g function? We look at the f function because we want to include the heuristic. If you choose only using the g function, in other words, when you get to this step here, you look at only the g function, then you're looking at a variant of the Dijkstra's algorithm because you're completely ignoring the heuristic. Is that okay? So the part of the algorithm, A star, that makes use of heuristic is how we choose when there are alternatives in O and we want to figure out which one should we choose. Dijkstra's algorithm does not take heuristic into consideration because there's no heuristic, right? So it's just picking, well, whatever seems to be the closest at this point to the destination. Yep.
So at this point, we're looking at the B and C values in the F.
Right.
Say, for example, they were the same.
Uh-huh.
How would it decide?
Then you just flip a coin,
It would just pick.
you can just randomize. Yep.
Okay.
You can either randomize or if there's any type of ordering within the vertices, you can just use that order. It doesn't really matter. The algorithm does not specify.
Okay. So it doesn't matter if they're the same.
Correct.
Okay.
Yep. Okay, but in this case, they are different. And because B has a lower F value than C, we're going to choose B. Is that okay? All right. So we put a B here, and then we remove B from the set. B is still in it. C is still in it. So now we have to look at all the outgoing edges from B, and therefore we consider all the neighbors connected from B as well. So do we want to consider vertex D first? It doesn't really matter. The order should not matter. Okay. So let's do D first. So now the question is, what is the T value? So the T value, once again, is how much does it cost me, or what is the length of the shortest path to get to B so far? It's 4 at this point, and then plus 2 because the edge going from B to D has a distance of 2. So 4 plus 2 is 6. So we put a 6 into T, and then we ask, is that smaller than the current G value of vertex D? Well, vertex D still has a current value of infinity, so it is smaller. So now we get into the then statement, and we add D to the set O first. So we have CD here. And then we update the previous. So D's previous is going to be who led to D. Come on. B. Yep, that's right. Okay. And then we update the G value to be just T. So T has a value of 6. So this now has a value of 6. And then the F value depends on the heuristic. So it's going to be 6 plus the heuristic of D to F. And we chose the heuristic of D to F to be 0. So in this case, the F value and the G value will turn out to be the same. Are we okay so far? Yes? Okay. So now we are looking at the other vertex that we can also go to from B. The other vertex we can also go to from B is vertex C. Okay, so we write down here. And what is the new value over there? Well, we could get to B using a distance of 6, but the edge going from B to C, okay, I think I misspoke. The current shortest path to B is 6, but from to B, from B. The current shortest path from the start vertex to B is 4. Oh, did I say 6? Okay, I misspoke. It's 4. And then from B to C has a 0 edge, a 0 distance edge. So currently it would be 0. 4 plus 0 is only 4. Okay? But now we have to look up the current G value of C. The current G value of C is in this column. And it says 1. Is 4 less than 1? 4 is not less than 1, so we have failed the condition of the conditional statement. So we have failed this conditional statement here. The condition is false. So that's why we don't have anything to update. So we did compute the value of T. That's how we found out that, nope, we did not find a shorter path. And as a result, the loop here is not doing a single thing. Okay. So now we are done with that iteration, and we're getting back to the algorithm. We got C and D to choose from now. Vertex C has an F value of 5. Vertex D has an F value of 6. So we're going to choose vertex C to be variable C in the algorithm. Is that okay? All right. So we choose vertex C to be variable C, and then we remove that from the set, so we only have D remaining in the set O. And now we have to look at all the outgoing edges from C. C only has one single outgoing edge to vertex E. Okay? And we have to compute the T value, which is based on the G value to C, which is 1 at this point, plus the distance of the edge CE, which is also 1. 1 plus 1 is 2, so we put a 2 here. And now the question is, well, did we find a shorter path to get to E? According to the G value, E still has an infinity as its G value. So yes, we did find a shorter path to vertex E at this point. So we get into the conditional statement. We get into this part here. We update O, so we need to include E into the set. We update previous, so that E has to go back to C. C is the previous of E. We update the G value, so that the G value is the same as the T value, which is 2. And then last, we update the F value, which is the G value plus the heuristic. The heuristic we chose to use from E to F, the destination, is 3. So we have 2 plus 3, which is 5. So this is the scenario that we have at this point. Do we have any questions about the algorithm? Yes?
I think this question was answered earlier, but let's say C had another arrow pointing to another vertex. You had two options with C.
Mm-hmm.
You just have to choose one, right?
Then you have to consider all of them. In other words, you will have another row to look at the other vertex that C is also going into. Yep. But since it does not have any, we only got one edge to look into.
Why is it 5?
Huh? Because it's 2 plus 3, because the heuristic from E to F is 3. That's how we chose. Yep. Mm-hmm. So are we good so far? All right. Cool. Cool. So now we are back to the while loop, and the while loop is still asking, do we have at least one vertex in O such that its f value is less than the g value of the destination, which is f? And the answer is yeah, because we have some vertices in O, but we also know that g of f is still infinity. Anything is going to be less than infinity, so we kind of know that, oh yeah, we have to go through at least another iteration. Okay, so now we go through another iteration. The first thing we need to do is to choose, so who is going to be variable c this time? In other words, of all the vertices in O at this point, D and E, which one has the lower f value? We got D and E, and you can see how E has a lower f value. So that's what we're going to choose first. Okay. Yes. So according to the algorithm, you can see how we choose C in O such that for all W in O, f of C is less than or equal to f of W. So we're choosing the one that is the smallest. Now, if there are two that are tied, then choose one or the other. Doesn't really matter. Which was a question that you asked earlier. It was, what if they are the same? So in this case, we choose vertex E to be our variable C. And now we have to look into, we have to take it out of the set first. Now we have to look into, okay, what are the outgoing edges of E? E goes to F directly. Okay, so we'll, or do you guys want to go to D first? It doesn't really matter, I mean. Which one do you want to look at first? Go to F first? Okay, well, it doesn't really matter. Okay, so we look at the G value to E, which is 2, and then we look at the length of the edge that we're considering, which is 4, has a distance of 4. 2 plus 4 is 6. So we put a 6 here, and then we ask, is that less than the current G value of F? Well, yeah, because the current G value of F is infinity, so it is less than. Yep. So the G value of E is 2 at this point. And then the 2 plus the 4, which is the distance of the edge from E to F, gives me 6. Is that okay? All right, cool. So we do have to update because 6 is less than infinity. So we do have to get into the then portion of the conditional statement. So we now put F into the set. Okay, so dF is my new set. And then we have to update the previous. So at this point, the previous of F, which is kind of saying that the current known shortest path is going from E to F. Okay, we know that is not the actual shortest path, but but at this point it is. So the previous of F is going to be E, and then we update the G value to be the same as T, which is 6, and then we also have to update the F value. Then you guys might ask, well, since F is the destination, that's kind of like a special case. Nope, we just consider it just like any other vertex, because we still just compute whatever the G value is, which is 6, plus the heuristic of going from F to F. The heuristic of going from F to F has no choice but to be 0, because it cannot be negative, okay? And it cannot overestimate. So it has to be 0. So 6 plus 0, guess what? Is 6. So we put a 6 here. Is that okay? Because that finishes the update of all the things related to vertex F. So at this point, we have found a path from the start vertex to the destination vertex. Is it the shortest path? No. So now the question is the A-star algorithm to go back and say, wait a minute here, that is not the shortest path? So we'll see, okay? But we got one more vertex to look at first. So we got the other vertex that E is also leading into, which is vertex D. And then we ask, well, what is the length of the path from E, from the start vertex to E and then to D? The length of the shortest path to E currently known has a length of 2, right? And then 2 plus this one is a 3. So T is only 3 in this case. Now the question is, well, is that lower than what we know about the shortest path, or what we know about the length of the shortest path to D? Now that part has scrolled off the screen already, so I'm going to scroll back to that portion of the screen, and that's a 6, right? So the length of the current shortest path to D has a length of 6, and this path only has a length of 3, also going from the start vertex to D. Did I find the shorter path? Oh yeah. Okay. So if that is the case, we got to go into the conditional statement because this condition is now true. So once again, we put D back into the set. It's already there, but that's okay. Okay, we are just kind of adding it back in. And then we have to update the previous. So this is the tricky part because D already had a previous, but we are going to update it and go like, whatever we said about how to get to D before was wrong. Here's the correction. Get to D through E. Is that okay? This is how the A-star algorithm can kind of go back and fix itself. Okay? Whoops, I found the path that I found to this vertex was not the shortest. Now we got a shorter one, and this is how I updated. Okay? And then we got a few other things to update because we also have to update the G function, which is just T, which is 3. And then we also have to update the F value, which is 3 plus the heuristic from D to F. And we definitely got an underestimate here, which is 0. So 3 plus 0 is also just 3. Are we okay with this update? Okay, cool. Okay. So now we move on because both of the outgoing edges from E are now considered. So now we go back to the main algorithm. And then we ask this question again. Do we have at least one vertex in O that looks kind of promising? In other words, its estimated, the length of its estimated shortest path through that particular vertex is less than the length of the shortest path currently known to the destination. Okay? So the answer is yes. Okay, because if you look at the F values that we have at this point, both D and F are in the set O at this point, but F of D is only 3, but G of F is already 6. 3 is less than 6, right? So that means we have at least one vertex in O that satisfies that requirement. Is that okay? Does everybody understand why we cannot terminate yet? Because the condition of the while is still true. Is that okay? All right. So we get into the outer loop again. We have to choose something to become my new variable C. So of the two left, okay, which is D and F, which one has the smaller F value? Vertex D, we just kind of looked at it. So we take that out of the O set, and then we look at all of its outgoing edges. D only has one single outgoing edge, which has a distance of 2 to F. So now we say, okay, it goes to F, and we have to compute T. So the value T depends on G of D in this case, which is 3, plus the distance of the edge dF, which has a value of 2. 3 plus 2 is 5. So we put 5 into my variable T. There we go. And is 5 less than the G value of F at this point? Yep. Cool. So that means we are getting into the conditional statement. So we are getting into these 4 statements inside the conditional statement. So we add F into the set O again. But because this is a set, we do not have duplicate items. So F is only going to appear once. But we also have to update all of the other things that we know about F. The previous of F is updated to be D. So this is how we make that correction. Okay? Because we thought that the shortest path to get to vertex F is through vertex E. Guess what? We were wrong. We just found a shorter path going through vertex D. So we're going to fix it. Then we go to the G values. G value is the same thing as T, so that's one of the easiest thing to update. And then we also have to update the F value. the f value is the g value plus the heuristic. But in this case, the heuristic of f to f has to be 0, so it's going to be just 5. Yep.
What's your previous value for C right now?
The previous value of C right now is A.
Okay. Thank you.
Yep. Okay, so we have now considered the only outgoing edge of D, and we're done with the for each loop. There's nothing after the for each loop in the while loop, so now we go back to the while and reevaluate the while statement. So let's focus on that statement again. And the question is, of all the elements in O, well, O only has one element now, which is F. Do we find at least one of them, okay, targeting O, F again, because that's the only element left in O, is the F value of F less than the G value of F? No, because they are the same. 5 is not less than 5. Uh-oh, we don't have anything that meets the requirement of having the F value being less than the G value of the destination. What should I do? Get out of the while loop, we're done. Well, not quite, but close to. We're out of the while loop, which is the main portion of the A star algorithm. The question is, did we find the actual shortest path? Well, let's find out what's going to happen next. So we define the solution graph, G, Sx. So what it's going to look like is we look at all the previous, and then we use all the previous to form edges. So if we have the previous of W being V, then we form the edge VW in, in the edge set. So now the question is, if I were to create this new edge set, I don't have a space for it in the spreadsheet. I'm just going to use the last row to represent it. Is that okay? Does everybody understand what this is going to be representing? Okay. So I'm just going to say E and then from A to F, okay, in subscript. What is that going to be? It's a set. We know it's a set. So we have to look at all the previous. The previous of F is D, so we have DF as an edge. The previous of E is C, so we have CE. The previous of D is E, so we have DE. The previous of C is A, so we have AC. The previous of B is also A, so we have AB. The previous of A is unknown, which is not a vertex, so we cannot put that into the set. So this is going to be my solution graph. Now, the solution graph does contain edges that are useless, right? Because unlike Dijkstra's algorithm, which finds a shortest path from every vertex to a destination, A star only finds the shortest path from one start vertex to one destination vertex. Is that okay? And our start vertex was vertex A, right? So if you want to know how to get to the destination, just give me a second. So you start with AC, and then once you're at C, there's only one choice, which is CE. Once you get to E, you only got one choice. Uh-oh.
That was my question.
Oh.
DE and not DG.
Did I make a mistake somewhere? Huh?
I think you meant to put B somewhere, you put E or something.
No. I think it has to do with going backwards. You have to figure out the shortest path backwards. So you have to go from the destination F back to D, and then from D. Oh, you're right. I made a mistake somewhere.
It was in the previous one somewhere, like, I looked at one of them and it had E when it should have had, like, B.
Oh, okay.
D.
Okay. Let me extend this a little bit. So it's probably when.
You see in column D where it has an E there, but I don't think that like is right.
No, that should be right because we're going from E to D. And then we look up E. E goes back to C.
Well, yeah, but that means that
And then C goes back to A. So that's good. That is.
that means that when you're going from the previous, you go
Yeah, so we have, no, we have the edge D, wait,
From E to D. That should be the edge ED, right?
that's from E to D, that is correct. Oh, okay, so when we wrote this, I wrote it incorrectly. So instead of DE, it is ED. You're right. Okay, there we go. Okay, so we started with F, F goes back to D, D goes back to E, E goes back to C, and then C goes back to A. So that's how we reconstruct the shortest path. So the construction of the shortest path is from the destination, and then you track the edges back until you get to the start vertex. Yep.
Why is the tuple AD in there? In that step?
It's just because B, because that edge is still somewhere there, even though it's not on the shortest path of A to F. At some point in time, we had that update.
Okay. And then the ordering of the tuples within the set doesn't necessarily matter, or
No, it does not matter,
okay.
because nothing, the ordering of things, elements inside the set does not matter. Yep.
So if you just wanted the shortest path back, would you do what you just did, where you trace from the
Yeah,
destination back?
yeah, you could do it that way. Yep. It's just like in cisp440, you just use the back pointer to track backwards. Yep. But if I were to reconstruct the entire quote unquote solution graph, that's what it looks like. But of all the edges, only a few are useful
Why is that the solution graph if it has extra edges, though?
because it still contains the solution.
Okay.
And not only does it contain the solution, but there's only one path from the start vertex to the destination vertex. So it does have some other kind of miscellaneous, edges in the edges, but they should not interfere with the shortest path.
Solution within it.
The solution is within that graph, correct? Yep. So do we have any questions about the execution of the A star algorithm? No questions about the A star algorithm? Yep, go ahead.
The variable t is always like what you see on the graph plus what your heuristic is. Is that
No, not the heuristic. So the value of t is computed here, which is the length of the shortest path to C plus the distance of the edge from C to N. In other words, t would be the length of the quote unquote shortest path from the start vertex to C then to N. Now the question is that path shorter than what we already know about N? If that path is in fact shorter, then we have some stuff to update. On the other hand, if this is a path but is no shorter than what we have found already, then the condition would have failed with the conditional statement. Then we don't have we don't have anything to update in that case. Are we doing okay so far with this algorithm? So I'm not going to do it in the class, but as an exercise, you can use exactly the same graph, but run it through Dijkstra's algorithm, so that you can have one being A star and one being Dijkstra, and then you can compare and contrast the two algorithms and really kind of understand how they're different, and and also not only how they're different, but what is the implication of the heuristic function. Yep.
So, like on an exam, would you want us to show it like that, or like write it down?
I would definitely want it to be shown like this. Yeah, because if you show it like this, it is clear to me, whether you could follow the algorithm and catch the algorithm. Like at this point, the set O is not empty, but yet we are getting out.
should we bring our laptops here
Hmm?
on a spreadsheet then?
I will give you a format like this, so you just fill in the blanks. Lots of blanks.
But in that case, we wouldn't want to use 0 for the heuristic function. It's gonna
Well, that's one thing you can try, right? Just use exactly the same graph, but then you use 0 for all the heuristics and see whether it makes any changes. You can also try your best to trick the algorithm to choose a path that is not the shortest and see how it corrects itself and go like, wait, you just led me to the wrong path. I'm going to fix myself here. Because it always knows. as long as the heuristic function is not overestimating. If you have a heuristic function that can potentially be overestimating, then it won't be able to do it. It won't be able to do its job. You can also try one more run where the heuristic is exactly the shortest path. Okay? In other words, your heuristic function is 100% informed. Then A star would be pretty easy because all it does is to go like, okay, I'm going to choose this. When I'm here, I'm going to choose that. And when I'm here, I'm going to choose that. And every single time it chooses, it's the correct decision. Because if the H function reflects the actual length of the shortest path from a vertex to the destination, then it will make the right decision every single time. On the other hand, if H is 0, if the heuristic function is always returning 0, then it boils down to about the same thing as Dijkstra's algorithm, but it's not going to be the same because the direction is different. A star starts with the start vertex, and then Dijkstra starts with the destination vertex and going backwards. So do we have any questions about either algorithm, Dijkstra's algorithm or the A star algorithm? Which one do I don't know whether they use one of those algorithms, because there are other considerations. So Google may choose to optimize and choose, some algorithms other than either one of these. But I would say it depends a lot because in Google's case, okay, even though your search is only asking what is the shortest path from this point to that point, but Google is you're not the only customer of Google, right? So as such, Google may actually want to pre-compute, the other shorter paths too, but it doesn't know, where the destinations would be because everybody has a potentially different destination. So I think Google does formulate the shortest path as you requested, but the way it comes up with the shortest path is probably something not like Dijkstra's or nor A star algorithm. They might have some different algorithms to do it. The reason why I said that has to do with if you just think about local navigation versus a say national, not even continental but national navigation. Okay. So I'll give you an example of what I mean by that. So let's say we want to go from a state capital to another state capital, but they're far apart. Okay, so Sacramento. Okay, go to maps. And then we look at Sacramento and pick a particular place.
The capital.
The capital, okay. Right there, right? Okay, so we click that. And where are we going?
Washington, D.C.
Okay, so where's my directions? And where in Washington, D.C.? The White House, how about that? We want to encourage our president a little bit more. Oh, White Cloud, okay. And there's such a place. The White House, the White Cloud, what's the difference? Okay, so the White House, does it know the White House in D.C.? There we go. Yep, there we go. Well, it didn't take it much time to find out how to get there. So if you, 42 hours, yes. So that's like if you drive nonstop and you have a fuel tank that can refuel your car while driving. We borrowed that technology from the Air Force, right? Then it will take you 42 hours. Of course, this is the next idea for Tesla, and I'm giving this idea for free to Elon Musk. Recharge on the fly while driving. But what if I'm in the middle of Nebraska where there's no infrastructure whatsoever? Not even a bathroom, right? I mean, so yes, so I think that would be a great idea is for Tesla to have these, recharging, stations that are mobile, and it would just connect to a Tesla, vehicle, and recharge it while both vehicles are running on the road. Yep.
You could just buy a Tesla for every stretch of 300 miles. And then you just get out of one, you just jump from one Tesla to the other. Just have them open the back hatch.
But you will still be losing time unless you want to jump while both cars are running.
Yeah, yeah.
Just like get you and
Of course we are.
get you and a buddy, and your buddy in the passenger seat will have a bunch of tanks of gas and a tube leading into the gas tank with a funnel. So he just pours it in, and it goes in the tank. And then if you need to sleep, you
Yeah.
can switch spots, like put it in cruise control.
And you'll have a third buddy to be smoking at the time. Yep. But 42 hours. But the point is, if you think about, this. Okay, let's look at the details, right? It's not like it just kind of loosely know which highway to take. It knows exactly how to get there, right? So if we look at now, where do I find that? Actually, okay, I think we click on this, and then we click on the. So it knows how to get to. I think this part is on the other side, right? This is in DC, direction in DC. Yep. So it knows exactly how to get there, from all the local turns in Sacramento to all the local turns in DC. So if you think about that search, if you think about all the alternatives, right, there has to be a lot of alternatives along the way. Many of those may not be very good ideas, but nonetheless, even the A-star algorithm will occasionally consider it's like, well, should I take this, branch or take that branch, right? So, I think Google uses an algorithm that is not A-star to do the shortest path.
I would have imagined they might have used Dijkstra's from particular locations and then cached them.
I think Google does a lot of caching, but the cache has to have a lifetime because traffic pattern changes, and the direction and the estimate does reflect traffic conditions. So they probably keep a local cache of pre-computed values already, and then keep those around for I don't know 5-10 minutes or whatever seems to be correct for that time frame of the day, and then reuse those values instead of recomputing everything. And that's how we can get things done so fast, because some of those entries is like, okay, we already know this stretch of this road for sure from here to here, the shortest path is blah 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 blah. So that's how we can do it, kind of faster and faster. That approach does use up a lot of memory or storage, but how much is storage or memory these days, especially when you look at it from the perspective of Google? Not a whole lot, right? I mean, they can afford to have enough memory to do all that stuff. Probably so. So are we good with these things? So let me use the next 10 minutes to talk about a problem that is similar to this, but not exactly the same, okay? So imagine you are a person driving for a pizza place, okay? So you're pizza delivery. And you have a few stops, okay? So let me just kind of present that in a different window here. So let's say you're driving a pizza delivery car, and there are 5 destinations that you have to go to. So A, B, C, D, E. Those are your destinations. So you start from the pizza shop, you have to somehow get to these 5 stops and then get back to the pizza place. And you want to find out, okay, what is the fastest way to do that? Okay, sounds pretty reasonable, right? But that is not something that the shortest path algorithm can solve, not by itself, okay? Because if you think about these 5 destinations, if they're all lined up It's pretty easy to figure out, okay? Especially if they all round up as a circle around the pizza place, that's easy peasy. You only got two real choices. Should I traverse it as A, B, C, D, E back to the pizza shop? Or should I traverse it as E, D, C, B, A back to the pizza shop? Easy, right? But it becomes a harder problem when your pizza shop is in the middle and then you have the 5 destinations almost equal distance from the pizza shop. Then it's like, okay, maybe A, B, C, D, E, back to the pizza shop, or some kind of general random order. So now the question is, how many different ways can you arrange the route as far as which destination should I go first? This relates back to an earlier thing that we talked about in this class, permutations. Permutations. You got 5 things to choose from, and I want all 5, right? Unless you want to eat 2 of those pizzas and only choose to deliver to 3 destinations. Then it becomes 5 choose 3 and lose your job. So if it's 5 choose 5 as permutations, then the number of possible ways to do the permutations or the ordering is going to be 5 factorial, which is 120. So you have 120 ways to start from the pizza shop, traverse all 5 destinations, and then back to the pizza shop. Does that make sense? Okay. So then between the 2 destinations, so let's say one particular permutation is in fact A, B, C, D, E. Then you can use the shortest path A star or Dijkstra's algorithm to find out, okay, what is the shortest path from A to B? Makes sense, right? What is the shortest path from B to C? What is the shortest path from C to D? And so on. Then you can actually figure out the shortest path for the entire traversal. Is that okay? Now this problem is also known as the traveling salesman problem, okay? Which is a very classic and important problem in computer science. So let's just say that you wrote that algorithm, okay? You wrote it in, I don't care, JavaScript, okay? And then your pizza shop owner is really happy about it, okay? Because compared to guesstimating just based on the driver's experience, you save the company a lot of money because most people overestimate, or they chose a way of traversing that's taking like 45% more time than what your algorithm can produce. Okay, so it's all good. And then one day your boss called you into the office and say, "You're fired." You go like, "What? What did I do? I just saved your company like a lot of money by optimizing how to traverse pizza stop destinations." Your boss said, "You embarrassed me because I took your program and I shared it with one of my buddies and it doesn't work." Okay, when my buddy ran it, it just did not work. You go like, "How? What? I mean, we know this program works. I mean, we have been using it for 2 months already. We know it works." And then you ask a little bit more and you ask, "So which one of your buddies did you share the program with?" That guy who owns UPS. Go like, "Okay." The boss says, then you ask a little bit more. It's like, "How is my program not working? Did it crash or did it give you the wrong path or what?" Your boss said, "It just didn't give me an answer. We started the program, it just seemed to be hanging up and doesn't come back with an answer." You go like, okay. So how many stops does a typical USP truck has per day, right? I mean, because that kind of calculates the permutation stuff, right? And then your boss says, "Well, it's somewhere between 150 to 200, okay, stops." That's a lot of stops. Well, I mean, you can estimate, right? How frequently do UPS trucks stop? Especially in a high density area? I would say every few minutes, right? So let's say it's every 5 minutes it has a stop. So in 1 hour, it has, what, 12 stops, right? So 12 stops per hour, and let's say you have 6 to 8 hour shifts, okay? 8 times 12 is close to 100. So let's call it 100, okay? 100 stops per day. How many different ways can we order those destinations when you have 100 stops? Your boss says, "How bad can it be? You guys got 5 stops, they got 100 stops 20 times, okay? So it cannot take that much time for this program to run. And then you try to explain factorial, right? It's like, no, it makes a big difference. 5 factorial versus 100 factorial, that's a big difference. And the boss says, no, that cannot be. I mean, 5 is 5, 100 is 100, off by 20. So now eventually you have to pull out a spreadsheet. I think it will do it. It will be a scientific notation, but I think it can still figure it out. Yes, so that's 100 factorial, as opposed to 5 factorial, which we already know, right? So the factorial of 5 is 120. So you look at the ratio. I mean, I know it's pointless, but we'll still do it, right? This is the ratio. So let's say it only takes 1 microsecond, to solve the case of 120. Okay, so how much time are we talking about here? So we'll be looking at this number times a microsecond, which is 1 times 10 to the power of -6. So you'll be looking at this many seconds to solve that particular problem. So we now look into, there are 60 seconds to a minute, 60 minutes to an hour, 24 hours to a day, 365.25, okay, rough estimate here, of days per year. You'll be taking this many years to solve that problem. No wonder the boss said, it did not come back with an answer, right? So your boss has decided to fire you because your program does not work with UPS. What are you going to do? What if you like that job because you got free pizza? Or you can educate your boss if he or she is one of those people, and you can say, this problem is NP complete. Okay? Your boss is going to say, there will be 2 things your boss is going to say. One is just pack your box, right? But the curious boss, like my kind, would ask, what is NP complete? So you dig out NP complete from Wikipedia, and as it turns out, every single problem within that classification of problems have the same kind of time complexity, which is the factorial of the size of the problem. And no one has ever solved those problems using a more efficient algorithm. Okay, all the smart people. Okay, Dijkstra, Knuth, Turing, von Neumann, all of those ingenious people have not solved the problem. So the chances that your boss may hire the next person, and that person turned out to be the person who can solve the problem and does not mind working at a pizza place, is pretty slim. Okay, so that is how you can explain to your boss and go like, okay, this problem is NP complete. There's no way to solve that problem fast. Now, are there other algorithms that can help with UPS? Probably. You can probably cluster the destinations. Like, if you look at all the destinations, okay, these things are all kind of clumped up, solve that sub-problem. If all of these things are clumped up, solve that problem. If all of these destinations are clumped up, then you run the overall algorithm to go from one clump to another clump. Is it going to give you the absolute fastest route? Probably not. But it will still give you a really reasonable solution before that much time runs out. Okay, is that okay? So this is just an exposure to NP completeness. Okay, and then some of you will probably be thinking, so what is NP? Not possible? Right? Mission NP? Impossible, right? Mission NP? No, NP is it's very peculiar. It only stands for non-deterministic polynomial. You go like, polynomial. What does that have anything to do with factorial and stuff like that? So the idea of NP complete is, if you can spin off a new core, a magical new actual core of the processor indefinitely, Like you can spin off as many cores as you possibly can in no time. Like the spin off part takes no time at all. It will still take each processor core polynomial time to solve the problem. That's what NP complete means. Huh? Yep. Those problems are also known as intractable. Can they be solved? Yes. But in practice, no. All right. So I'm going to leave the lecture at that, and I'll see you guys on Wednesday, where we'll start a new homework assignment on the search algorithms.